At this point, I'm hoping that you've watched the 3 videos for the fundamentals of probability. We're now going to be going into some of the details, in particular the discrete variable probability. There's a lot of details in probability. So what I've done is I've made sort of a probability map of all the different topics within probability. So we're going to do a little overview for this whole probability unit. And once we've done that, we'll talk about discrete versus continuous, and then how to calculate, single random events. Let's look at this probability map, because I do like kind of seeing what the big picture is, and so we can kind of plug what this discrete variable piece looks like. All right, so here we have our probability map. We've already talked about the fundamentals of probability at this point in time. These are the basics which are really true regardless of what aspect of probability we're talking about. The first big division is this discrete versus continuous. And really it's going to be continuous independent variables, although I'll generally say just continuous. All right, so we're going to be over here an awful lot. It's going to take a while to work through all these various aspects of discrete variables. All right, the next division is going to be dependent versus independent. And we'll talk about, what that means after we finish with discrete. Dependent, we have mutually exclusive, which is also known as disjoint events, or not mutually exclusive, which is also known as joint events. We have independent variables, and we have 3 different situations for independent variables. This isn't the only 3. These are just the 3 we're covering in this class. And then we're going to jump back over here to continuous. And there's going to be all kinds of different forms, similar to binomial, geometric, and Poisson. These are 4 very typical continuous distributions. They're not the only ones, but they're the ones that we'll cover in this class. Now, what I've done, this is attached, an attachment on the website you should be able to find and print out. I would recommend that you do that so that you can keep track. It's easy when we're talking about all these little details and these equations. You kind of lose track of where you are. So I think it's pretty helpful to keep this handy so that you can see where you are. And by the end, you're going to need to be able to identify any particular question. What type of question is it? Is it down here? Is it over here? Is it over here? And so to kind of help you out with this one, here are some examples which you should get in the habit of doing. One particular question, might be a discrete independent Poisson. Another one might be discrete dependent mutually exclusive or continuous normal distribution. You just have to start thinking about how to sort of triage a question and see kind of what path you need to follow so that you can answer it appropriately. If you don't know that it's Poisson, then you won't use the right equation, right? Because it's all a lot of details in probability. So we just talked about the probability map. Again, what I would do is print that up from the website, keep it handy so that you can kind of check things off as we are going to do it. So as we start looking at what is the difference between discrete and continuous variables, let's put an example up on the board. Let's flip a coin 5 times. So the real question is, can you see 3.5 heads? The answer, of course, is no. You either have 3 heads or 4 heads. And I know there's the whole, the coin resting on its side, thing that students always love to bring up. But in fact, that's not heads anyway, so it wouldn't even count. So The answer really is no, and that's what distinguishes a discrete variable. No in-between values, right? That's what discrete means. Here's some other examples. Number of students. Hopefully we can't have 7.5 students. Die roll, it's going to be 1 through 6, assuming a 6-sided die. Number of countries, etc. The things that really aren't divisible, and you simply won't get any in-between values. So, alternately, continuous variable, we're talking about an infinite number of in-between values, such as height. A person could be 5'10", 5'11", 5'10 and a half, 5'10 and a quarter, anything. Weight, the amount of caffeine in a coffee cup, milligrams, temperature, could be 28 degrees, 28.2 degrees, 28.25 degrees, infinite number of in-between values. So when you're presented with a probability question, the first division, like I showed you on the map, is, well, are we talking about discrete or continuous type of variable? At the moment, we're going to focus on discrete variables. We'll get back to continuous after we spend quite a long period of time actually talking about all those different kinds of discrete variables, geometric, binomial, mutually exclusive, non-mutually exclusive. We'll get through all that, and then we'll come back to the continuous variables. So now that we're going to be focusing on discrete variables, let's actually figure out how to calculate the probability for a single event. Let's look at an example. What is the probability of seeing 2 heads if a coin is flipped 3 times? Or, alternatively, I suppose, a set of 3 coins is flipped once, which in the end is really the same thing. So we're continuing with our coins. That's a really classic discrete variable. So it's a nice example to use for demonstration of principles. Now, there's 2 ways of approaching determining probabilities for something like this. Experimental and theoretical. Experimental probability would be actually doing the event, in this case, flipping the coin a bunch of times and keeping track of the outcomes. Theoretical would be not actually doing it, but creating some theoretical model that predicts what might happen. Right? Both actually use the same basic concept of what probability means. And that is this simple ratio, outcome of interest over a total. And I've written this out as generically as possible because when we start talking about experimental, we're going to actually change the wording of this to kind of fit the fact that we're performing an experiment. When we talk about theoretical, again, we'll take the same ratio concept and change the wording of it so that it matches theoretical modeling, right? But this is kind of the underlying concept, which should hopefully make sense when we start talking about experimental probability. For our example of the set of 3 coins, if we want experimental probability, we could flip the set of 3 coins 60 times. Now we're going to get lots of different outcomes, but what's our outcome of interest? Well, our outcome of interest is whenever 2 heads are showing, so we just keep track. We have a tally sheet, and we say, well, of the 60 times, how many times were 2 heads showing? Maybe for this experimental run, 2 heads showed 23 times out of the 60. So, our probability of seeing 2 heads would, of course, be 23 out of 60. A lot of people intuitively understand this. Now, hopefully, this makes a little bit more sense. We have our outcome of interest, and we have our total. Outcome of interest, and we have our total. Now, like I said, we could rewrite this in a more experimental kind of wording, which would look something like this. Number of favorable outcomes, right? Favorable is the ones we're looking for, our outcome of interest. Total number of trials, because we're actually doing an experiment, right? We've done 60 trials, right? Trials is just like in the quiz example in the other videos. Every time you took a quiz, right, that was a trial, right? So it's a set of random events. Well, we have a set of 3 random events because we have 3 coins. And so we have 60 trials total. Now, when we look at theoretical probability, we have something which looks maybe like this. I left the top blank for the moment. This concept of total, we can then think of as sample space. So the total number in the sample space, how big is the sample space, is our total, because that's all possible outcomes. Well, what's going to be the outcome of interest? Well, only a certain number of these, if we're, again, talking about coins, we're going to have, 3 heads, and we're going to have, heads, heads, heads. We're going to have heads, heads, tails. Here, I'll write this out. All right, that might be one combination. Maybe we have that combination. Maybe we have this combination. All of these are going to be in our sample space, and a lot more. Well, some of them have 2 heads showing, which is our outcome of interest. So the way we could write this, perhaps, number of combinations of interest. Because we're now building, again, this theoretical model in which where there's only a certain number of combinations of heads and tails. We could get our sample space, and then we just see how many show 2 heads. We, of course, have to be very careful about constructing our theoretical model. There's always assumptions when you make theoretical models. For example, is this a fair coin? Right? If it is, then heads and tails are equally likely to happen for any one single event, which means each one of these combinations are equally likely to happen. Well, that's pretty important information. Like, if they weren't fair coins, and it wasn't 50-50, then we might get actually quite different probabilities for the different combinations. So we just have to make sure that we know what assumptions we're making when we build a theoretical model. In trying to actually calculate this theoretical probability for this particular example, seeing 2 heads out of 3 coins, the question is, what do we need to know? Well, we've already identified really what we need to know. The total number of combinations, and of course the number of combinations that show 2 heads, right? This is going to be our ratio, this one over that one. I put this one first because if we could figure out the total number of combinations and what they are, then it will be pretty easy to just pick out the ones that have 2 heads. So I'm going to show you a technique which is going to be actually really useful, not just for this, but when we get into dependent variables, it's going to be very important. And that is a tree diagram. And what we'll do is we'll start off with a single point. And all tree diagrams really, this is our starting point. And we have flip number 1, or actually what we really should do is change that to coin number 1. Right? This is our first coin. Right, because being theoretical, we're not actually flipping the set, really. We're just saying there are 3 coins. What are the combinations? And so what can happen with the first coin is, of course, the first coin can show a head or a tail. Well, what about coin number 2? Well, if it's heads on the first coin, the second coin can, of course, be either heads or tails. And the same is true if the first coin was tails. The second coin could be heads or tails. And you can hopefully see what's happening when we start dealing with coin number 3. It's really just a repetition of the same thing. The third coin can be heads or tails based on all of the previous events. So here's our combination tree. And again, we'll be using this as a probability tree, and it's structured really very much the same. Well, what are all the possible combinations? Well, what we can do, here, I'll use this. Well, this is one combination is like that, which would give us 3 heads showing. Well, what about a different combination? Maybe it would be this, this, and that. We can essentially follow all the branches to find all the combinations. And I'm going to start running out of color soon. We've done all of these branches, so what we'll do is we'll move down to this branch and come up here. Hopefully you can see that's going to be heads, tails, heads. And then this is going to come here, here, and here, which will be heads, tails, tails. And continuing, we'll have tails, heads, heads, tails, heads, tails, 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 heads, and of course the final one, tails, tails, tails. Having finished filling out this whole tree, notice that what I have here are all possible combinations. So this is my sample space. And how many are there? There's 1, 2, 3, 4, 5, 6, 7, 8. All right, so we have 8 total. I'm going to maybe put it down here. Total number is 8. And then what we can do is how many show 2 heads? Well, that shows 2 heads. That one. That one, and looks like maybe that's all that show 2 heads. Let's see, number showing 2 heads, all right, is 3. So the probability of 2 heads would be 3/8, or 0.375. Which is, of course, that same theme of, outcomes of interest over total. In this case, we have total number of combinations, number of combinations that show 2 heads. When we went over the probability map, remember, talked about the probability checklist, which is kind of mapping out, where this is. Now, we haven't covered all of the map yet, but I just wanted to, let you know. All right, we're talking about, this is a discrete variable. Under discrete, it's also an independent variable. And binomial. All right, so this is a very specific case, and even more than binomial. It's essentially a 50-50 split because the coin is 50-50. That's not always the case. I mean, what we'll do is we'll study binomial distributions when it's not 50-50. So this is a very specific case, which is important because different cases will have different relationships. You'll build this ratio in different ways. But underneath all of that, wonderful detail is still just this concept in which, I should have mentioned this, this is known as relative frequency. when you create this ratio. That's the relative frequency. And it gives you a decimal number, which, of course, if you want chance, you can make that a percentage pretty easily.